So this sequence of slides represents common content between GCSE Maths and GCSE Physics. So you are effectively revising this for two subjects. On this slide we've got the relationship between distance, speed and time. It doesn't matter which of the three versions that you learn, as long as you learn one of them. If we were to learn, say, the distance equals speed times time, then it's easy to derive the others. If you divide both sides by speed, you would end up with the time is the distance divided by the speed. And if you divide both sides by time, you're going to end up with speed is distance divided by time. Now this looks exactly like the previous slide, except it's regarding velocity rather than speed. And so we have the same style of equations, but this time we've got rather than distance, we've got displacement, and rather than speed, we've got velocity. So our equation this time is displacement equals velocity times time, and then the derivative two equations are also given there. This and the following three slides are a selection of questions of the style that you might get given in GCSE Physics or GCSE Maths. The solutions for these are given towards the end of this video. It's important that you can recognize what is going on in a distance time graph. So here are three examples which might come your way. You either have to learn these, or in the exam you'd have to interpret them from reading off the axes. Some people find that easier than others. So our first one there just shows the distance staying exactly the same. So that means the object is stationary, it's not moving. The other two have got an angled line, one with a positive gradient, the other with a negative gradient. So in the one in the middle there, you've got the object is gradually getting further and further and further away from the observer at a constant amount each second. So this object is moving away at a constant speed, otherwise known as a uniform speed. The other one, the third one there, has got the object gradually getting closer and closer to the observer because the distance is gradually getting smaller and smaller. Again, it's happening at a regular amount every second. So this is the object moving towards the observer at a constant speed or uniform speed. In both of these, in all three of these, if you measure the gradient of the line, you will end up with the speed. So in the first one there, the gradient is 0. The object isn't moving, therefore the velocity is 0. In the second one, if you worked out the gradient will be a positive number, and in the third one it will be a negative number. These two graphs do not have a constant gradient. The gradient is changing. So in the left-hand one, the gradient is starting steeper and then gradually flattening out until the gradient is 0. And therefore we can interpret that as being an object slowing down and then stopping. So that object is decelerating. To the right we have one where the gradient is a certain amount and then the gradient gets steeper. That implies that the speed is getting greater, and therefore this object is speeding up or accelerating. So both of those show non-uniform speed. The speed is changing as the time is going by. So here we have a distance time graph which is divided into three sections. From the previous slide we know that we can tell that the first section that's the object, that represents the object going away from the observer at a constant speed. The second section, that's the section at 5 meters, that's flat with a gradient of 0, therefore the object is not moving. And then the third part there, the object is coming back towards the observer. So we could interpret it in that way. We can also interpret it in terms of the speeds of those 3 different sections. So in the first section, the object is going 5 meters in 4 seconds. So that will be a speed of 5 divided by 4, which will be 1.2 meters per second. In the second part there, we've got the object is going 5 meters towards the observer, and the object is taking 8 seconds to do that. So this time distance divided by time, 5 divided by 8, and that would give us a speed of 0.625 meters per second. Now, strictly speaking, if we were talking about velocity, that would be a velocity of minus 0.625 meters per second. So this and the following 3 slides are for you to get some practice at interpreting distance time graphs. And again, I give you the solutions to these at the end of the slides. Question 1. Displacement is a vector, speed is a scalar, velocity is a vector, and distance is a scalar. An object can have a constant speed and a changing velocity if it is moving in a curve. In other words, its direction is changing, but its speed is not changing. Because velocity has got the 2 components, the speed and the direction, means if the direction changes, the velocity changes, even though the speed is staying the same. Question 3. Your typical speeds here for cycling, 6 meters per second, running 3 meters per second, and walking 1.5 meters per second. And then the equation relating speed, distance and time will be speed in meters per second equals the distance in meters divided by the time in seconds. So our car is driving 16 meters east, followed by 25 meters south, followed by 16 meters west. Easiest way to deal with this is to draw a diagram. As you can see here, the distance is nothing to do with the direction, so to find the distance you'd add the 3 distances together and get a total of 57 meters. The displacement is the straight line distance between the starting and ending points, and that's drawn there for you in green. And so we're starting at the starting point, ending up where we're ending up. That's 25 meters, and it will be in the direction south. Now this sort of question I've seen more frequently on a GCSE Maths paper. It gives you some information about 3 stations, normally called A, B and C. And I've always found that the best way of doing this question is to draw yourself a diagram, put on your A, B, C there. And then there are 3 things we are involved in here: the speed, the distance and the time. The question is going to give you some of that information, and you're going to have to work out the rest. So you are given from A to B, you're given a speed and you're given a time. So we can work out the distance by multiplying those 2 together. And then on the other side there, from B to C, we're given the speed and we're given the distance. Now you'll notice in the question that the distance is given in kilometres, 16.8 kilometres, so you must change that into metres before you can proceed, otherwise you're going to end up with muddled answers. So that converts to 16,800 metres, your speed is 60 metres per second, and you can do your distance divided by your speed, giving you a time of 280 seconds. You then add your distances together, add your times together, and then you do the speed as the total distance divided by the total time, which will give you an average speed of 55.5 meters per second. Here we have a distance time graph, which again is divided into three sections. We've got a first section with a particular gradient, a second section where the gradient is now greater, so the line is steeper, and then a third section where the line is flat. So we know first of all that that flat section is going to be where the object is staying still, not moving anywhere, it's staying 60 meters away from the observer as the time goes by. So we better conclude that the object is going away from the observer at a certain speed, then it's speeding up to a different speed for a while, then it's staying still. Now you're not going to have any problem with the first bit, so the first bit there, it's gone 20 meters total in 8 seconds. So to find the speed, you do 20 divided by 8, and that will give you 2.5 meters per second. It's the second bit where some people make a mistake, and they think that they're going to use the total, that's the 10 seconds, and the total time, that's the total distance, that's 60 meters, and they do 60 divided by 10, and that of course is not correct. That would give you your average speed in the first 10 seconds rather than the speed in that steeper section. So you have to take the difference in time, which is just 2 seconds, from 8 to 10 seconds, and the difference in the distance, that's from 20 to 60 seconds, that's 40. So your two figures are 40 meters, 2 seconds, distance divided by time, 40 over 2, giving you a speed of 20 meters per second. So here our object is coming towards the observer. So it started 50 meters away, it's coming towards the observer, then it's staying still by the observer, and then it's going away again. This time the gradient of the first section is greater than the gradient of the last section, so we'd expect the speed to be greater for the first bit than the third section of this graph. So to work out the speeds, for the first part we're doing, the object is doing 50 meters, so that's from 50 to by the observer at 0, and it's doing that in 6 seconds. Distance divided by time, 50 divided by 6, that's going to give you about 8.3 meters per second. For the other one there, you're going from 10 to 16 seconds, so that's 6 seconds, and in that time we're going 20 meters, so it's going to be 20 divided by 6, and that's going to give you about 3.3 meters per second. So this sort of question is assessing whether you really understand what is meant by 10 meters per second. So if something's going at a speed of 10 meters per second, it means that every second they're doing 10 meters. So our line will begin at the coordinates 0, 0, and we know that in the first second we're going to do 10 meters. So we can plot the coordinates of that point 1, 10. In the next second it does another 10 meters. The coordinates for that point would be 2, 20. In the third minute it would go up to coordinates 3, 30, and in the fourth it would go to the coordinates 4, 40. We're then staying still for 2 seconds, so that means that we do a horizontal line from 4 seconds to the 6 seconds, and then we're returning going 20 meters per second. So that means from 6 to 7 seconds it will go from the 40 meters away to the 20 meters away. So that's the coordinates for that point. And then finally in the last second from 7 to 8 seconds it will go from the 20 meters away back to you. So the coordinates there will be 8, 0.